But it's my distinct pleasure to introduce Brian Z. I'm going to call you Brian Z. Brian Zahnstecher. And Brian, if you can come up while I'm talking, I'll just briefly introduce you. So Brian is the principal of PowerRox. He's been with many different companies, Cisco, HP, spent most of his career, I think, in servers, data centers, and obviously power in various forms. I know, like his other cohorts here, very interested in energy harvesting. And he co-chairs the IEEE Future Directions Initiative and specifically co-leads the 5G Roadmap Energy Efficiency Working Group. He does that with Francesco, who I'll introduce before the panel. But it's a great honor and a pleasure to have Brian come and talk to us about some of his thoughts, learnings from the past, and where he sees this going in the next 5 to 10 years. Brian.
All right, thank you. And yeah, thank you very much, first off, to Sujit and CWC and Mark for the invite and everything here. And just a quick clarification there, too, in terms of yeah, my partner in crime there, Francesco, co-chaired the Energy Efficiency Working Group of this INGR, essentially this roadmap deal. Which is part of the IEEE Future Directions, the Future Networks things, usual IEEE, hierarchies and acronyms and stuff can be kind of confusing. But anyways, yeah, and thanks also for the talks from Colleen and Mark. Actually, for the most part, I think they covered it all pretty well. So aside from saving me time, I'll just say, what they said. I was telling Colleen, I like the name of her. Our talk, the Green Point O. So maybe this is more like the, Green Point O. And so the idea here today is what we're going to talk about, kind of a couple really key concepts I want you to keep in mind. And something that, I've certainly observed over my career, whether it's working in data center, or bigger in hardware, or, ultra low power energy harvesting, microwatt type of systems, and anything in between, is that we try and stick to kind of more the concepts that apply from the micro to the macro level. You hear me say that a lot. And so, some really key concepts of that again, were touched on in several different ways, both more articulately and probably with much better graphics than myself, from Mark and Colleen, right? Or, the idea of just certain things like, just because you can doesn't mean you should, right? What he was showing there in terms of always keep in mind, there's rarely there's an assumption that there's some linear relation between performance and power or energy utilization, and that really actually in reality is rarely the case. So the concept of being migrating from an old kind of, in my opinion, old school philosophy of always on to always available, which I believe I coined from Ericsson actually originally, is kind of a much better way to go. Because like you said, the number one way to save energy is to turn something off, but the next best thing is to operate at the most efficient way versus your efficiency curve and all that. And so yeah, well, the bad news here is we're not going to give you the answers to all this stuff today. Ideally, we're going to kind of provide more of the big picture, a better way to assess this stuff, a methodology for looking and thinking about these things, and then a framework for the assessment. And the call to action for you is hopefully you guys will be the ones to help us actually use this stuff and make something useful out of it. So with that, we'd also just like to mention one of the purveyors early on. Lest we forget to honor Earl McCune, who was part of our working group originally and also part of Eridan as the CTO when he unexpectedly passed away a couple years ago. So just shout out to Earl, always trying to make the world more energy efficient. And a snapshot there, that is our effort, our working group. Here's a big roadmap chapter, I think something on the order of 120 pages that essentially tries to capture just about everything my predecessors discussed. You can see we're in good company. Along with myself, and this stuff is all pretty freely available online. This started with just kind of a concept discussion, led to a white paper, and then Francesco and I once we realized, there's enough stuff here. We got to break this out in a full-on working group. And as you know, especially in the volunteer world, if you mentioned it or suggest it, you own it. So That's just me and a bunch of junk I do. I don't even talk about that. So just a heads up too, just to highlight that a lot of this stuff, if I mention, people, companies, products, I mean, I personally am an independent consultant, but this is not, this is not meant to be a specific endorsement or advertisement for anything, so we're unbiased here. Sometimes we use examples that we think serve as good examples, but just for the lawyers in the room. Okay. So what we're going to talk about today is we're going to start with kind of, like I said, kind of the more some conceptual things just to help us visualize, wrap our heads around the big macro problems, how to tie it to the micro, and then also introduce maybe some metrics, and then to be able to articulate that stuff, and then we're going to introduce it into a framework, as Mark also excellently segued to before, a systems approach. For assessing this stuff. So as he also mentioned, kind of here's the big picture. This is for the U.S., and I was trying to convert in my head when you were asking about terawatt hours to quads, because that's how the EIA puts it out every year. I think it's something like 3,000 terawatt hours per quad, or something like quadrillion BTUs, or whatever. It's a lot of energy, right? And one of the key things I always like to start any talk with, whether I'm talking about this stuff or energy harvesting or whatever, it's to realize that at the end of the day, almost 2/3 of all raw sources of energy. This doesn't like my angle that I'm working at here. It ends up going to what they call rejected energy. We might commonly refer to as waste. And just another kind of key concept to always keep in mind: when you think of something as waste, where do you put the maniacal focus in? Right? How do you get rid of it? But if you think of it as a resource, well, that completely changes the calculus on your total approach to it. And I'm going to skip over this stuff pretty quick because it's been mentioned several times. Essentially, big energy footprint. The whole ICT. Whatever 60-80% is in the RAN. You break that down in the base station, right? A good portion of that's in the PA, typically the LPA, the linear power amplifier. So we focus on the areas of lower hanging fruit, and this is advancing by itself. So even they want me to hurry up. This is a big picture thing, and I know it's kind of an eye chart, though. Thanks to this comically large screen, you can actually almost see it. But the whole point, and this comes from one of our working group members at Aerodent. There, it's automatically advancing. Damn it. And this is just kind of showing a difference, comparing, consumption from looking at like a macro base station to a micro one, and over a different range versus power. And kind of the key takeaway from all of this is we need to kind of, we need to combine how we look at, what I think is more commonly spectral efficiency type of metrics, right? And combine them with actual energy efficiency, actual utilization metrics. Right, so in something like this, maybe we need to look at something like, gigabit per area unit area, gigabit unit area per, like say watts per, megahertz or something like that. And yes, that is as, as conflated as it sounds. But really, just kind of another key concept, right, is the idea of really focusing on the big picture, right, the embodied energy, as Colleen pointed out, but also to do it in a way that it's done, like I said, again, looks at the big picture. And you can see, as many of the charts that Mark was showing, you can commonly see that while efficiency may increase in something, in general that I've experienced in my career, from tiny systems to global ones, power footprint never goes down. The power never goes down, right? And that's the biggest differentiator, why we need to understand the difference between, the embodied energy, the big footprint, the big picture, and saying, oh, well, this box here, this black box in a long string of black boxes got a little better. But, often it's playing whack-a-mole. It's usually just going from one spot to another. And if you're not looking at the big picture, and the people who run are responsible for those black boxes are siloed and not motivated to work with each other, then we kind of gotta force the hand a little. And so that's a big part of what our work is about. So this is another one we kind of already know. Where all our power's lost to, and we'll represent this graphically here soon, but mostly in the RAN, thanks to loss from our freeze transmission here. And in general, like Mark was saying, you whatever 10-15% or something in transmission is lost getting from the power plant to the base station. But then thanks to that LPA, that's why the base station itself is horribly inefficient. And then of course it's orders of magnitude worse when you're going to the edge. And so a couple concepts that we want to introduce to understand this is one, something we call a power value chain. So what this means is we take a string of anything. You follow something from generation, from source to load, to end use, right? And you connect however that you get from source to load. That is a power value chain. And I'll show this graphically in a second. And a metric to understand, which is one of the most important things that I always come back to, aside from auto-advancing slides, is this metric of power cost factor. And so what this is an important part to understand. This will help us understand the cost of energy, but the real key point, again, is at the point of utilization. Okay, a watt at the edge is not the same as a watt from, at the power plant, and the cost of that. And so that's what we really want to bring focus to. So graphically, kind of in the 5G sense, right, a 5G power value chain might look something like this. We're generating in the, sorry, I got to get at a weird angle to get this thing to, okay. At the power plant, and it may go through some, transmission. Here we have the RAN section, which we know can, which is where we kind of get from kind of linear drop to start getting nonlinear. And on the bottom is this power cost factor metric. And so what this means is that we're looking at it from the perspective of the edge, right? So this would say that if the user equipment energy was generated at the point of consumption, right? For instance, for example, like say energy harvesting or something for your UE, then that would have a power cost factor of 1x, right? But if that same amount of that tiny power had to go backwards through all this, the actual cost factor, I don't like your clicker, could actually be 5-6 orders of magnitude. And so in other words, even if you're consuming the same bit at the edge, what actually has to be generated, as you can see here, can vary quite greatly. And this is the bit about the point of consumption being absolutely so critical in these analyses. And so, another thing we want to highlight is that, something that's overlooked, and I think a lot of times when people, when you want to assess, whether it's energy consumption or energy efficiency, people tend to kind of separate big power stuff and tiny power stuff. And that's another part of our work that we wanted to highlight and make the connection to, is that actually these things are inexorably tied to each other. Whether it's a sustainability aspect of saying we're already, by the number of edge devices we're deploying, which I know the definition of a thing can certainly vary semantically, but damn it, I swear, these are not my, I didn't put these timings in here, unless you're screwing with me up there, and you're doing a good job. But the point, even in today's standards, we're really on the order of throwing away close to 100 million, primary batteries a day now. And so, there's a big argument. I won't spend too much time on energy harvesting stuff, but there are good justifications that are not just sustainable, but that are also, even financial and come with financial and business justifications as well. So just kind of a quick point to that, that power value chain and that power cost factor is just saying that, certainly the tinier power the stuff is, the more the opportunity is for utilizing energy harvesting. But, we make an argument that at scale, because of the power cost factor, if all that stuff had to come from more upstream, that, as we scale to the billions or even, a trillion of these, edge devices, that it could even literally impact the, have an impact at the grid level. So another concept we put in something called, which is just codifying that, which is one we call the 5G energy gap, which is saying that, so much available, so much demand from the edge of all these tiny power devices, like I said, could actually impact something at the macro utility level. And then a slight difference on that is something called the 5G economic gap, which says that, as we know, it doesn't matter if the load demands infinite power. Typically most systems and stuff are usually power thermally limited, right, to protect themselves or whatever. And so what that means is that they are going to cap the application, if you will. So it actually becomes an economic gap, right? Again, just because you can doesn't mean you should or will be able to. And so what this is saying is that for power and thermal utilization reasons, hardware will have to throttle itself and that means that the predicted use case and how many users it'll handle or how much traffic or whatever, right, actually ends up getting bottlenecked by power and thermal considerations. And so when you consider the economic payback models that went into these massive deployments and CapEx investments, it puts a very different spin on it. So we like to look at everything through the lens of what we call the universal currency of energy. We figured the best way to attack these very difficult problems was to translate into something common. And for us, the energy, we figure we can translate anything into energy. And if you look at our roadmap chapter, these are kind of the main areas that we focus on and try and tie together. I'm going to hurry up and kind of go to the more graphical version of this instead of just talking to it. Essentially, right, it's how do we picture all these black boxes and get them to talk to each other. And ultimately, we want to culminate in another metric we were introducing, which is called 5G D-rate factor. So kind of like if you're familiar with PUE from the data center world, right? It's an oversimplified metric that just says, okay, just give me an idea of understanding how much energy is utilized by my true load, my IT load in this case, versus the overhead required. And so in this case, we're trying to give a D-rate factor to say, well, is one thing you may have designed your network and your system and all to achieve X amount of this or service X amount of users or traffic or whatever. But again, for power and thermal bottlenecking reasons, you're actually limited to something much less than you expected. And so that's how we're trying to help kind of articulate the characterization and quantify this stuff so that we can optimize in the right places. And lest we forget too, and we don't have time to kind of dig into the bigger impact, but it's also part of our work is to also tie it to the socioeconomic impact and something we call the 5G equality gap. So here's the big picture of the black boxes, right? Literally, this is an example of one for 5G systems of systems. And what you'll notice is that it's not just hardware, it's not just software things. There might be things that are kind of considered less, more intangible, like standards or regulatory constraints, right? And when you want to assess a power value chain from end to end, right? How do we look at, there are obvious ones like we looked at like power transmission, but if we said we wanted to look also at the impact of a change in the 3GPP, the next generation of the spec, how can we actually quantify that into energy impact? And that's really the main goal of this system. So what we decided to do was to take something that's, create a black box, the template, where any one of those black boxes could represent anything, whether known or unknown, right? This is meant to be a modular framework where we can take whatever, figure out what the unique intrinsic inputs are to that specific block, but we can translate that all to our universal currency. And here's an example of what, say, for instance, a black box for a base station might look like under the hood. Now we're getting from a framework assessment to, how do we actually model and simulate this? Because again, we're not giving you the answers. We're merely trying to provide the methodology for wrapping your head around it and the assessment. So in an example here of say it was a small cell base station, some of the inputs that might go into that are listed here. I'm not going to read it for you, but the point is too, in looking at the operations, there are many, many more, but we're only concerned about the ones that kind of really, the knobs that really move the needle for power consumption, right? And so, here's this is just an arbitrary example so you can kind of understand how the framework works or is proposed. And so, maybe based on these inputs and stuff that, we say that this block might have these outputs of, and there's some arbitrary numbers just to together what something like that produce. And then we do first what we call a static chain analysis, where we just look at all the individual black boxes. So if this was a power value chain, of a network, for instance, you can see with the power cost factor approaching, 5 or 6 orders of magnitude, this is edge stuff, right? And then this might be more like base station type of stuff. This might be more like utility distribution. So if we were to assess this, and even just so using some really basic assumptions to make the math easy, you can see that, for instance, here, it says that even if this base station, for annually costs, has a 10,000 kilowatt hour load or whatever, and costs roughly $20,000 in OpEx for the year, and then we can see also that that'll generate just how much power needs to be generated to support that. Now, conversely, here's something at the edge, this little tiny power device. Now, it may be a half watt load, but it could still cost that much a year if the energy had to be generated from the same source upstream. So, and again, could still have almost half as much needs to be generated as this supposedly huge load because of the point of utilization. And then lastly, kind of what this will all culminate in is this dynamic chain analysis where, this is the real meat of it, where hopefully it has value to you folks, where we challenge you to make use of this, right, is to say, now this is where we can really do the what-if scenarios and try and optimize stuff. So if we take these static models and then we put them, compare them to what our desired network performance targets are, right? What are the inputs on that? Whether it's limitations you have by the available amount of power, or how many users you want to serve, or payback period, and even taking into account the dynamic price of the real-time energy market, and say, well, once you add all these up, one, is it as optimal as it can be, and what does that mean? Right, so we'll say, the way you've wired up this power value chain, it consumes X, Y, and Z, and here how much we think it'll cost, and this is what we say is the max achievable 5G D-rate factor. And then we'll want to put it in our optimization engine and say, can we now improve upon that better? And once we're done, this is what we'll say is what we say theoretically based on, again, power and thermal metrics, which is your absolute the best you can do. And now everyone has a target. For a realistic target to try and harmonize the business and technical worlds. So again, don't have time to get into it, but just we didn't want to leave the socioeconomic disparity and what communication and energy does to enable lives for people. But we can talk more about that offline. So, in conclusion, right, key takeaways. Right, tiny devices at scale can actually cause big problems at the macro level. Driving energy efficiency is not a nice to have. We got to get beyond that. Everyone agrees, makes mention of it, pays lip service, but we want to actually propose how to do something about it. The migration to small cells and things is a huge opportunity and a potential game changer. But people ask me all the time, so is it better to go to small cells? Is it going to use more or less energy? And I would say it's a much more difficult problem than the jury's out, because each one may use much less power, but there's going to be many, many more of them. So more data is required there. And really just, you got to understand the power value chain from the lowest level to the biggest one to truly characterize it. And we propose doing that through the common currency of energy. And so that's where our framework that I had to blow through there is about, but it's a modular one. It's a new block of clay, and we want you to help us mold it. So with that, thank you very much. And like I said, we'll save the question stuff for the panel. And just know that there are, in the materials that are being shared, there's, many, there's about another 50 slides or something like that dig into a lot of this stuff in more detail that we didn't have a chance to go through. So thank you very much.